In this video, we prove the second lemma that we used in our discussion of the Heckman selection model from an earlier video. This lemma says that the expected value of v2 given x and y2 equals 1 is equal to the inverse Mills ratio evaluated at x prime delta 2. In other words, a standard normal density evaluated at x prime delta 2 divided by a standard normal CDF evaluated at the same argument. This proof really has just two steps. In the first, we determine the conditional distribution of v2 given x and y2 equals 1, and in the second, we apply a result for truncated normal distributions that's proved in a separate video. We want to determine the cumulative distribution function of v2 given x and y2 equals 1. In other words, the probability that v2 is less than or equal to some threshold t conditional on x and y2 equals 1. Substituting the participation equation, we know that y2 equals 1 if and only if v2 is greater than minus x prime delta 2. So we can replace the y2 equals 1 in the conditioning set with this alternative expression. Now, by the definition of conditional probability, the probability that v2 is less than or equal to t, given that v2 is greater than negative x prime delta 2, and given x, is equal to the probability that v2 is less than or equal to t, and v2 is greater than minus x prime delta 2, conditional on x, divided by the probability that v2 is greater than negative x prime delta 2, conditional on x. Recall that v2 and x are assumed to be independent. Thus, we can drop x from the conditioning set in both the numerator and the denominator, leaving us with the following unconditional probabilities. This is a point where you may find things somewhat confusing. I find it helpful to actually substitute in a value for x, so we could call it curly x. The point that we're trying to make here is that once we've fixed x, minus x prime delta 2 is just a constant number. So we're evaluating the probability that v2 falls into certain ranges determined by some constant number c, and those probabilities do not in fact depend on the random variable x. So adopting the shorthand, c is defined as minus x prime delta 2, we see that the probability we've set out to compute is precisely the probability that v2 falls into the interval c to t, including t and excluding c, divided by the probability that v2 is greater than c, which is, of course, by the definition of conditional probability, precisely the probability that v2 is less than or equal to t, given that v2 is greater than c. So what we have found after all this hard work is that the probability we set out to evaluate, which conditioned on x and y2 equals 1, doesn't actually need to condition on either of these two. It's enough to simply condition on v2 being larger than this quantity c, which is considerably simpler. From the previous step, we've seen that the distribution of v2 given x and y2 equals 1 is the same as the distribution of v2 given that v2 is greater than c, where we've defined c to be minus x prime delta 2. Thus, the conditional expectation of v2 given x and y2 equals 1 is the same as the conditional expectation of v2 given that v2 is greater than c. And because we know from assumption c that v2 is a standard normal random variable, applying a result for truncated normals that's proved in a separate video, the desired expectation is equal to phi of c divided by 1 minus phi of c, where little phi is the standard normal density and big phi is the standard normal CDF. Substituting the definition of c, namely negative x prime delta 2, we obtain the following. Now recall that the standard normal density, little phi, is symmetric. This means that phi of minus c is equal to phi of c. Thus, we can drop the negative sign in the numerator. Similarly, by the symmetry of a standard normal, we know that 1 minus phi of c is equal to phi of minus c, where here I'm referring to capital Phi, which is the CDF. Thus, we can replace the denominator with capital Phi of x prime delta 2, giving us precisely the inverse Mills ratio expression that we set out to find.